All right, well, welcome everybody, both in real life and those of you who are attending virtually. Thank you for joining us in our continuing series on the decarbonization of architecture. Today, we're going to be talking about the electrification of buildings, which of course is a subset of decarbonization. And our guests who will be guiding us are Marco Alves, who is an associate principal at PAE Engineers, mechanical engineer. Welcome. And then also Alan Shepard, not the former astronaut, however, a principal at PAE Engineers. And just a reminder, for those of you who are AIA members, this is worth 1.5 CEs towards your zero net carbon design category, which is now a new requirement in our ever burgeoning growth of required credits for the year. So with that, I'm going to hand it over to our guests. And if you could just give a brief introduction background, we appreciate it. Thank you.
Thank you, Mike. So pleasure to be here today. So the subject of today's presentation is building electrification and decarbonization. This is the agenda for today. I'm going to just do a very, very brief introduction to PAE, and then we'll get into the meat of the presentation. Why decarbonize? Marco's going to talk about code implications, all electric technologies, architectural considerations, refrigerants, embodied carbon, and then carbon offsets. And hopefully we'll have a bit of time for Q&A. I would ask if you could put your questions in the chat for people who are online. I think the plan's going to be for Marco and I to try and get through the presentation in 40 minutes, then we'll have a Q&A at the end. So PAE, we've been around for over 50 years now. I think it's 54, 55 years at PAE. We've got 365 staff, predominantly on the West Coast. Our head office is in Portland, and then we've got offices in Seattle, Eugene, San Francisco, Spokane, and we just recently opened an office in Los Angeles. So exciting times. Our sort of core business, core disciplines are mechanical, electrical, and plumbing engineering. But we also provide sort of sustainable consulting and energy analysis through our Regen group. We do technology consulting, commissioning, and architectural lighting through our Luma lighting group. We get involved in pretty much everything. So all kinds of projects we get involved with. And something we try to bring to every single project is a real commitment and passion for sustainable design. 100 LEED Platinum projects, 61 are all electric. That image there is actually our head office in Portland, which is a living building that we recently moved into. We're part owners in that, very small part owners in that building.
Very small.
Right.
Yeah. Okay, so like Mike mentioned, this is an accredited session. 1.5. We had 1 in here, so this needs to be updated to 1.5 credits. And if we go to the next slide, here's the learning objectives. Why electrification and building decarbonization is important. How to overcome barriers, understanding various technologies in building design towards electrification and decarbonization, and learning about embodied carbon as well as other types of carbon metrics. There's a sign-up link here at the end. This slide deck is going to be shared with everybody, so you can use this link after the session to sign up and get the credit. All right, so with that, let's dive right into the why decarbonize, and I think most of the people in the audience today are going to know why, but obviously to avoid the adverse effects of climate change, there's been an agreement, tentative agreement towards 1.5 C of global temperature rise, and in order to stay within that, there's an effort that needs to be done towards decarbonizing, not just the building industry, but the building industry plays a big role, and reduce greenhouse gas emissions by 20% of 1990 levels. So when we talk about greenhouse gas emissions, what do we mean? Well, let's talk about that for a little bit. So typically everybody thinks about CO2, greenhouse gases, but the reality is there's many gases that have a global warming potential. And so if We look at methane, which natural gas, it's about 34 times more potent than CO2, if you will. Nitrous oxide emitted by cars, for the most part, 300 times more potent. And then fluorinated gases that are used in refrigerants that make up a lot of the HVAC plumbing equipment that goes into buildings, thousands of times more potent than CO2. And CO2 is used as the metric. So when we say greenhouse gases, or we talk about tons of carbon CO2 equivalent, what that means is how many tons of carbon compared to CO2. So CO2 equivalent is a metric that you can see in a lot of the literature. So that's what this means.
Yeah, so methane, you would say, has a global warming potential of 34 times more potent than carbon.
So staying with methane, natural gas, which is used in buildings a lot to burn. So we burn gas to heat buildings, to boilers. We do it to warm up the water, to take showers, wash our faces. And so methane, or natural gas, has a pounds of CO2 equivalent per kilowatt hour metric of 0.4 when it's burned in buildings. And so the 0.4 and these metrics you may not be familiar with, but if you just keep your mind on that 0.4, that's without considering any leakage. So you get your gas at the building and you burn it, and that's the amount of greenhouse gas emission that goes into it. If you factor emissions, the fact that there's gas leakage in pipes, also in extraction methods, then we're at least up to 3%. And shale gas extraction, which is basically fracking, it's up to 8%. Now, the thing that's important to remember here is that when we get up to 3% leakage, use of natural gas in buildings is as harmful to the environment as using coal. Okay, so at 3%, we're crossing that barrier. So, and so this is important because we're going to talk about various components of carbon balance, and we're seeing in our industry a bit of a shift from net zero energy towards net zero carbon, which is a broader goal, if you will. So that shift, what does that mean when we talk about net zero carbon in a building? On the one side, you have emissions, so building a building and putting it all together is embodied carbon. Operational carbon is the carbon involved with the energy use, gas, electricity, or any other energy that goes into your building. And then you have refrigerant leaks. All of those are on the emission side. So you're stacking up your carbon when you first build and start to operate the building. On the flip side, you have offsets. So putting PV or generating renewable energy, as well as carbon sequestration, stays on the other side. So a building is carbon neutral when your offsets are equal or larger than your emissions over time. And so the first part of this session is going to focus on operational emissions, but we are going to touch on the other ones as well. And so going into the next slide, talking about operational emissions. You can see this graph here by the National Resource Defense Council. This is a path towards decarbonization in the US, and you can see transportation, industry, and building carbon associated with the energy use in those industries. And so overall, we're looking to get to an 80% reduction overall, so be at 20% of 1990 levels. But in the building industry, it's a much steeper amount of work to do. So we want to be at 10% of where we were at 1990. So how are we going to get there? So that graph showed the consumption on the building side for that building piece. And that's one side of the carbon. Right? The other side is how do we generate the energy and how does it transmit it? How does it get to the building? So the path towards carbon neutrality involves getting clean power for each of the buildings. And within California, there's a Senate Bill 100. And that Senate bill basically asks and requires that by 2045, all the energy generated in California has to be renewable, clean, carbon-free, right? So what that means is that if you have a building and so all the energy is going to be clean by 2045. So this is a big part of the decarbonization movement. Right? So when we look at the building side of the coin, and if you, so the bar here on the left, the green piece represents electricity, the gray one represents gas use in buildings. And so if we have a building that we're building today, 2020, 2022, and it has gas in it. If we don't get rid of the gas, what happens is that, so we can do a lot of work. Step one is demand reduction, so getting the energy efficiency down, being good envelope, efficient systems, and all of the things we're already doing, lowering the energy use of the building. But the next step is that if you still have gas within your building, you have a gas boiler or gas water heaters, by the time we get to 2045, all the electricity is clean, but the gas is still there. So we haven't decarbonized that building. And this is why it's very important to eliminate gas. Because if we go to the next slide and we electrify buildings, there's no gas in the building, and most of the buildings that we're designing these days are all electric. By the time we get to 2045, it's carbon free. Right?
Yeah. The challenge is that while California is trying to decarbonize the grid, we're adding load to that grid as well, because the heating that was done by gas boilers and gas water heaters is now going over to electric, and transportation as well. Cars are going over to electric as well. So as I say, at the same time you're trying to decarbonize the grid, you're actually putting more demand on the grid as well. So it's a real challenge. All right.
So let's talk about code implications. And so in California specifically, a lot of jurisdiction cities have developed their own reach codes. So this is something that's available to California cities. And many of them have developed their own reach codes, and they are all different. So they require electrification in general. They have exceptions for kitchens, some labs, healthcare, and the requirements for EV chargers are different. The requirements for PV are there, but can be different. So the big takeaway from this is that if you're doing a project anywhere in California, you need to really do your code research, because each city is going to have their own requirements. Now the link here, localenergycodes.com, is a California state link that will take you to all of these reach codes and will tell you in detail what's required for each of those. Now, when we switch from city codes to state codes, the challenge is that the California Energy Code, Title 24, 2022 version, as it's known, does not require electrification throughout. Multifamily buildings and commercial buildings are still allowed, and as not only are they allowed, the baseline includes gas. And so when you design an all-electric building, you're in fact being penalized in terms of energy. So how do we get around that? In this next slide, you can see here at PAE what we've done in the projects that we're working on. We have to do the baseline. We have to use the state software, which is CBAC-COM, which really cannot model a lot of the technologies that we're using, heat pumps, to electrify buildings. But you still have to use it, and you got to model the building as if it had a boiler and a gas water heater. And you will get a result like that that says fail. When in fact, the reality is that if you take that energy use at all of those hours of the year, so our regen team has created a tool which basically translates that energy as if it was being used by heat pumps, by the real equipment, with actual equipment curves of efficiency in all of the hours of the year, and it passes. Not only does it pass, it uses less energy than the baseline.
It's basically a post-processing to the output of seabed. We've gone to several jurisdictions and got it through already, and there's a couple in the works where we're working with the local authorities to get approval for that. But it's a bit of a crazy situation that on the one hand, California is all gung-ho for all electric, and then their mandatory code compliance software penalizes you for doing it. But that's where it goes.
So one thing would be, if you're doing an all-electric project, and the city requires you to do it, talk to the local officials, have that conversation early. How can we show you that we can pass with an all-electric design using the state software? Because that's the problem.
But you have to do it as an alternate means and methods
Yeah.
application.
It's like an exceptional count, yes, yes, yeah. And it really comes down to how sophisticated the person is, the individual that you're dealing with. Some really know what they're talking about, yes, they understand it, they're on board. Others are really scared about what you're proposing because they don't understand it. So it just depends on who you're dealing with. Okay, so I'm going to talk a little bit about all electric technology. What does it mean when we talk about all electric buildings? And basically, it comes down to replacing gas burning appliances like gas boilers, gas water heaters, and replacing them with heat pump technologies. That's really what we're talking about here. It also applies to kitchen cooking equipment where we're replacing gas ovens with convection combi ovens and induction cooking appliances. The replacements for gas boilers, on a lot of projects we're using air source heat pumps, and these are similar to air cooled chillers but can operate in reverse, so they can generate both heating and cooling. We look at geothermal systems as well, geothermal heat pumps, and on some projects we'll look at VRF as well. So all of those are all electric heating and cooling solutions. Gas water heaters, again, we'll use air source or water source heat pumps, and there has been a new technology which are CO2 heat pumps. The CO2 is actually used as the refrigerant in these machines. So that's another technology that we've been using. Gas versus all electric cooking. When the REACH codes first came in, there was a lot of pushback from kitchen operators and chefs, because they were used to cooking with gas. They didn't think that electric could do the job, but we have seen a gradual acceptance and a shift towards all electric. Google have gone that way. All of their kitchen facilities have gone all electric. And there are advantages in addition to it being more energy efficient and producing less carbon emissions. Electric induction cooking, conduction cooking, it's actually faster and more responsive than gas. And of course, because you don't have the emissions and the nitrous oxide gases and that type of thing, indoor air quality around that kitchen environment is improved as well. Okay, so gas boilers versus heat pumps. In the past, I've tried to explain the refrigeration cycle, and it never goes well, so I'm not going to do that today. But basically, everyone, a gas boiler, that's a device that uses a chemical reaction between fuel and oxygen. The output of that chemical reaction is heat, and the byproducts are water vapor, nitrogen oxide, and CO2. And the absolute best that a boiler can do is to take the calorific value of the fuel and to convert all of that into heat. And it's actually impossible to get to 100% efficient. The best boilers can get up to about 96%. A heat pump is a different animal altogether. It doesn't create heat in the way that a boiler does. It moves heat. And it uses, electricity goes into a compressor, and that manipulates the boiling and condensing points of the refrigerant, and that's what enables you to move the heat around. And I'm not going any further than that. But suffice to say, it's under a completely different set of thermodynamic laws to combustion. And because of that, you can get a heat pump that is 300, 400, 500% efficient. And what I mean by that is you can put 1 kilowatt worth of electricity into the heat pump and get 3, 4, or 5 kilowatts worth of heat out of the other side. what we call that a coefficient of performance. So if you put 1 kilowatt of power into a heat pump and you get 4 kilowatts of heat out, you would say that that heat pump has a coefficient of performance of 4. Okay. And then refrigeration machines, they're used in all different types of application, and they have different names depending on the application, even though the equipment is pretty much the same from one application to the other. So what we're seeing on the screen here, you've got a room there, the sun's beating down on it, it's summer and it's hot in there, it needs cooling. So we've got an air conditioner here that is drawing heat out of the room, cooling it, and then it's rejecting that heat to ambient air. This is an air conditioner, we will call this an air conditioner, and this would have an annual COP of about 3 on average. Here's much the same piece of equipment, but this is winter time. We've got a space that needs heating. So what happens here, the machine is sort of reversed. So it's actually extracting heat out of the air. So even though it's quite cold outside, it's 45 F, it actually extracts heat out of the air, cooling it down to 35 degrees. And then it takes that heat, amplifies it in temperature, and puts it into the space. And again, heat pumps would have a similar COP of about 3. So it's the same refrigeration system, it's a different application. The other one you would call an air conditioner, you would call this a heat pump. A really key factor that determines the efficiencies of these machines is something called lift. And that's the temperature difference between the outdoor air here, which is at 45 F, and then the temperature that you're trying to create on the other side, which in this case is 80 F. So in this case, this would have a lift of 35 degrees. Okay, and the smaller you can make that lift, the more efficient the machine operates. And that brings me on to the next example, which is geo-exchange. We've got our heat pump outside again, but instead of extracting heat from ambient air, it's now got a hydronic loop and coils in the ground. So it's trying to extract heat from the earth. And in this case, it's wintertime, but the ground temperature is still about 60 F. And what you've achieved here is the temperature differential, the lift, is now going from 60 F to 80 F. So it's reduced from 35 degrees in the previous example down to 20 degrees. And this makes that machine operate that much more efficiently. And that's really the whole purpose of geo-exchange. That's the whole benefit of geo-exchange, to reduce that lift. And again, so in this example, we typically see annual efficiencies for geo-exchange heat pumps of maybe 4.5. And then here's the next one. This is like the holy grail of efficient heat pump applications. And it's where, in all of the previous examples, only one side of the heat pump has been providing a benefit. So for example, when it was in cooling mode, you had a beneficial side cooling the space. The other side was just rejecting unwanted heat to atmosphere. Okay. Now this is an example where you've got a building that has a simultaneous demand for heating and cooling. So on the left, it's you've got a room there, it's receiving low angle easterly sun and it needs cooling. Okay. And on the right, it's receiving no solar radiation and it needs heat. So in this case, the heat pump is drawing heat out of the room on the left that needs cooling. It amplifies the temperature of that heat and pushes it into the room on the right and heats it. And because both sides of the heat pump are now provided a benefit, you'll get a COP of 7, sometimes almost 8. So this is like the most efficient way that you can use a heat pump. Now, at the individual building level, sometimes you'll only have a very small amount of that simultaneous heating and cooling time. But what we find is if you start looking at mixed use developments where you've got different types of buildings, you might have an office, residential, lab building, data center, and you bring all of the heating and cooling loads back to a central plant, because it maximizes that potential to have that simultaneous heating and cooling demand. A classic example is somewhere where your office building will need cooling. At the same time, your residential and if you've got retail, restaurants, they need a ton of domestic hot water. So you bring those loads together and then you meet both of those loads with that super efficient heat recovery heat pump. this is another example where quite often in buildings we'll find a scenario where you've got heating and cooling that occurs in the same 24-hour period, but they're sort of separated by 6 or 7 hours. So, you'll have a domestic hot water load on a morning, maybe the showers and food production, and then in the afternoon, the sun's out, you've got a cooling load. And a way in which you could take advantage of this is by introducing thermal storage. So in this example here, the heat pump is pulling heat out of the thermal storage tank, creating chilled water. And it's at the same time you're meeting that domestic hot water heating load. So that's heat recovery mode, the COP is 7. And then 5 or 6 hours later, you draw down on that chilled water store to meet your cooling load. So quite often, when you're working with engineers, particularly, as I say, on central plants and mixed-use developments, they'll be talking about introducing thermal storage into the system, at least for this reason. Okay, some architectural considerations. We've got our traditional sort of approach on the left, which is gas boiler, cooling towers, water-cooled chillers, and on the right, we've got a building with air source heat pumps. The key thing here that you'll see is that the air source heat pumps are quite big, bulky machines, so they'll typically take up more space than the cooling towers would have done. They're also pretty heavy, so there'll be more load imposed on the roof structure. And because they're refrigeration machines with compressors, they'll tend to create a bit of noise as well. So in noise-sensitive locations, if you've got a resi building next door, you've got to be really careful about locating the machines. The domestic hot water on the left, that would be done with a regular gas-fired domestic hot water heater. The one on the right is a heat pump water heater. And what we find is that with the heat pump water heaters, they'll be married up with a larger amount of storage. And it's to keep the cost of those heat pumps down, you use more storage. So your domestic hot water room will probably be a bit bigger than you're used to. On the positive side, you no longer have an indoor chiller room or a domestic hot water storage tank room. The other benefit, of course, is that the gas has gone all together. So you've only got an electric incomer on the right, whereas on the left, you've got an electric incomer and a gas utility. And this is just a little table that just shows some spatial comparison. So we took a typical San Francisco office building, 250,000 square feet, 6 stories, 500 tons of cooling, 3,750 MVH heating. And we worked up some space requirements. So on the roof, the all-electric air source heat pumps, we've gone from 850 in the traditional case to 1,250. The chiller room has gone, as I mentioned before, the domestic hot water room's got bigger with all-electric because of the larger requirement for storage. The gas meter room has gone. Your peak electrical load with all electric is going to go up a bit. Not as much as you think, but it does go up a bit. So we've got a slightly larger electrical room. MEP costs, the heat pumps are more expensive than gas boilers. So overall, we've been seeing a 5-7% cost premium for going all electric. There's the acoustic thing that I mentioned before. Something that's a little bit surprising is that the energy cost for going all electric actually goes up. And although, as I've described, the efficiency of air source heat pumps are far better than gas boilers, electricity is that much more expensive than gas, or at least it is at the moment. So that's why there is a bit of an energy cost premium. I think in future years, I can imagine that gas will be more expensive and the relative cost of electricity will probably come down. So that may well swing in the future. But the main reason for doing this, the operational carbon emissions of going to all electric, currently it's about a 25% reduction, just by going all electric on your heating. With air source heat pumps, there's no water use in the heat rejection, whereas if you've got a water-cooled chiller, you've got all that water going out through the cooling tower. And then this last line here is the heating of water temperature. Now, typically with gas boilers, you'll generate water at about 180 F, 160, 180 F, whereas an air source heat pump can only generate 120 F of water. So if you're doing a retrofit from gas boiler to air source heat pump, it's not as easy as all that. It's not just taking one out and plugging plugging in the new machine. You may have to increase your pipe sizes, your pumps, and it can affect your coils as well. If you've selected your heating coils in your air handlers for 180F, you won't get anywhere near the heat output if you go to 120. So, yeah, retrofits of existing systems can be tricky. Okay.
Yeah, so let's come back to carbon discussion. And so there's a lot of electrification, how we electrify buildings and that decarbonizes buildings. But now we're going back to carbon discussion. And so related to refrigerants, they have an impact, and it's mostly related to leakage. All right, so leakage of refrigerants. So we're going to talk about what does that mean. And so depending on the type of equipment, project, you have a certain project, you select a certain system. You go with a central system with a chiller or VRF that's distributed, etc., a single residential unit, that all has different implications. So depending on the system that you select, you're going to have more or less refrigerant. For example, VRF has pipe throughout the building, right? So if you're doing a multifamily residential or even small commercial, you go with the VRF system. There's refrigerant pipe that goes from those units on the outside to the units on the inside. That's filled with refrigerant. When you compare that with these larger units, this is the refrigerant here is centralized, so it's all contained within that piece of equipment. So there's two things that matter here: the type of refrigerant and the amount. Okay, so as we go to the next slide,
Yeah, so there's substantially more refrigerant with VRF, and because you've got all of that extra piping, there's a bigger chance of it leaking as well. Yeah. Oh, sorry.
Yeah. So as we look at this graph, you can see here on the right, the typical refrigerants that I use today, these two, R410, R134A. The thing that's important is to look on the left there, 100-year global warming potential of these refrigerants. So 134A is about 1,400, 410 is about 2,000. And so that's pretty high compared to some of the newer refrigerants called natural refrigerants that have much lower global warming potential. And one of the things that's happening now is that the California Air Resources Board came up with a ruling, this is actually fairly recent, where they're banning equipment that has refrigerants with global warming potential of 750 and above by the end of this year. So what that means is that a lot of the equipment that we're using in projects right now, these air source heat pumps, are using these typical refrigerants. They can no longer be used as of January 1st, 2024. So there's a bit of a market shift happening here with manufacturers and us. We're all working together trying to figure this out, but that's what's happening.
If you do have a 410 machine, you'll still be able to get hold of the refrigerant for quite a long time, but you won't be able to buy new 410A equipment. And it is a bit of a worry because the replacement equipment isn't commercially available yet when time's running out, right? And we've got long lead times.
So this next graph, which is the last on refrigerants, again, you see different types of refrigerants at the bottom, and you'll see VRF, which uses 410A. So like Alan said, there's a lot of piping distributed, and so that creates leakage. There's also a lot of refrigerant within that piping. So it's the amount of pipe and the propensity to leak. And so VRF would have a very large global warming potential impact. And this is in different units, tons of CO2 equivalent per kW, but it's basically like a global warming potential. When you compare that to some of the air source heat pumps that are contained, you can see that's much, much lower. And Alan and I and others are working on projects now where we're actually using air source heat pumps that use CO2 as the refrigerant. And so if you go to that, we have that here, but it would be very, very low. And even that, just to Alan's point about this evolving equipment, that piece of equipment, which is a CO2 machine, is being made for the project as a one-off. It's not commercially available, so it's being manufactured for this one project. Because we have a client that wants to go with natural refrigerant.
Yeah. It sounds really crazy that we talk about reducing carbon emissions, CO2 emissions, and they use CO2 as the refrigerant in the machine. But when you consider that the alternative to CO2 as a refrigerant is something that has a global warming potential of 2,000, you know, that's a very small leak of CO2 in the overall scheme of things is tiny. So,
How does the CO2 perform when compared to 410 and other?
it's good. There are certain peculiarities to it. It operates at higher pressure, much higher pressure. So so the piping has to be more robust, the fittings are more robust, and you need sort of like specialist maintenance people to look after the machine. So that's
higher electrical loads too.
no, the efficiencies are comparable, or in some cases better. So they're good machines, and I think it's we've seen some clients already going down that path. Genentech, they're owned by a company called Roche, and they've got like European standards. So they don't allow any hydrocarbon-based refrigerants at all. So at Genentech, you can use ammonia as a refrigerant, CO2, propane, you know, and it looks like they're going to go down to CO2. But Mark and I are just engineering a project with a CO2 heat pump machine. And then, you know, as more and more get installed, I think you'll get more and more specialized, you know, operators and maintenance staff who can look after it. All right. So the next piece of the puzzle, embodied carbon. So we've covered operational emissions, refrigerant leakage. The next one is embodied emissions, and I'll move to the next slide. So embodied carbon is all about the carbon that is emitted in creating the building in the first place, and then demolishing the building at the end of its life. So you can see here, first of all, you've got the carbon emissions associated with mining and extracting the raw materials. There are emissions associated with transporting those materials to the point of manufacture, to the factory. There are emissions in creating the various products and then transporting those products to the construction site. You've got all kinds of tools and equipment that use energy on construction sites that emit carbon. During the life of the building, you've then got the operational emissions and the refrigerant leakage that we've presented already. But then you've also got reoccurring embodied carbon due to maintenance, refurbishment, repairs to the building. And then you've got end of life, where you demolish the building and haul it away and all the rest of it. So all of these go into what we call the embodied carbon of a building. And it's significant. So this is showing global CO2 emissions. The blue in the upper right-hand side, that's building operations. The yellow is industry. The grey is transportation. And you see the embodied carbon there is at 11%. So that's a significant part of the total. It's major. Okay, carbon offsets. So we finished on the emission side of the balance. We're now going to look at the offsets. The first one, I'm just going to briefly discuss this, carbon sequestration. This is basically talking about extracting carbon out of the atmosphere, and really, we're talking about paying RECs, renewable energy certificates, to purchase tree planting. And as trees grow, they sequester carbon out of the atmosphere, and you can actually use that to sort of show how you're working towards carbon neutrality. So I'm not going to go into too much detail on that one, but it's an option. The other one is, of course, renewable energy, on-site PV, wind turbines, that type of thing. And I think you're all pretty familiar with the components of a renewable energy system. On the left, we've got the production side, we've got the PVs themselves, we've got the grid connection. In the middle, we've got storage and the microgrid controller, so that's your battery storage. And then on the right-hand side, you've got the loads that consume that electricity. And really what that battery does, it maximizes the carbon reduction potential of your PV. Because what you can do is, whenever you've got an excess of PV power, you can charge up that battery, and then you can choose to draw down on that store of power to meet the electricity demands when your grid is at its dirtiest. So it's usually at sort of times of peak load, you're pulling in power from out of state, from maybe, coal-fired power plants. That's when you draw down on your battery to meet your loads. So by doing that, as I say, it enhances the carbon offset of your PV system. The other benefit of battery storage, of course, is that you're reducing your peak load demand. So you've got a lower peak load demand for your electricity supply. And there's the resiliency benefit, of course, as well, that if your grid goes down and you've got a nice big store of power in your battery, you can keep your building going for a certain length of time. A key thing just to note is that if you want to use your PV and your battery when the grid is down, you need that microgrid control. That's the brains of the system. So you need that to get that resiliency benefit. Okay, this is my little carbon offset cheat sheet. And this is what I wanted to, so that all this is showing is how much PV you would need to offset your operational energy use in a building. And I've done it for different building types. So here we've got an office on the left-hand side, resi, laboratory. The EUIs here are 4550 and 150. These are sort of industry standard, not particularly great EUIs. It's yeah. And then what we're showing there is how much PV you need to fully offset the operational energy use of the building. So for the office, so I should take a step back. This is that same 250,000 square foot office building in San Francisco, 6-story, okay? And for the office, to fully offset your operational emissions, 330 feet by 330, resi 350 by 350, the laboratory has a much higher EUI, so that's 600 by 600. And another way of looking at this would be to say, if it wasn't a 6-story building, but it had the same footprint, how many floors could a PV array that covers the entire roof, how many floors could it offset, right? So for an office building here, it would be able to offset 2 floors of that office. So if a building wasn't 6 stories, it's 2 stories, you'd have a net zero energy building. Resi about 1.75 floors, laboratory only about 0.6 of a floor. What can you do to improve that? You could drive down your EUI, you can have a higher energy performing building. Here we've taken the EUI for the office down to 25, which is a pretty decent EUI for an office. Resi 30, laboratory down to 90. And you can see here the amount of PV that you need to get to net zero is now reduced significantly. And on the bottom, you can see the number of floors that you could have as net zero floors. So the office has gone to 3.5, resi 3, and you've now got a full laboratory floor that will be net zero. And then the last piece of the puzzle here is if you have the battery, which, as I said, maximizes the carbon offset potential of your PV. And now for the office building, we've got it up to 4 floors, resi 3.4, and the other laboratory 1.5. So it's just a little cheat sheet to see what you can do with PV. The next thing that we wanted to do was at PAE, we've got like a life cycle carbon tool, offset tool. And what we're showing here, again, it's our 250,000 square foot office building. And what this graph shows, the grey bar on the left, that's year 1, and that's the embodied energy of that building. Okay, this is a concrete building, standard sort of concrete building, and that grey bar is the embodied energy, embodied carbon. The green there is how much offset you would get from the PV array. The orange is your operational energy use from heating, cooling, lights, and so on. And the yellow is your refrigerant leakage. Okay. In this case, the embodied carbon is 60 pounds CO2 equivalent per square foot of the building. The heating cooling machine is a heat pump with R14A refrigerant. And the PV area is 264 by 264. And what we're seeing here is the PV, to get to a life cycle net zero output, the PV has to generate more energy or offset more carbon than the sum of your operational and refrigerant leakage. That's the deal. It has to be positive in that way. And if it is positive, year upon year, it will gradually draw down and pay off your initial embodied carbon. So the blue there represents the balance gradually being worked down over like an 18-year period. It's like paying off a mortgage. Yeah, yeah. And in this case, we get to life cycle net zero there at year 18. That's when you've fully paid off your initial embodied carbon, and beyond that, you're like life cycle positive. Yeah. The next, we just ran a few of these just to show how you can manipulate all of this. So then the next example was where we said, right, how would this graph change if we improve the EUI performance of the building and make it more energy efficient? You know, higher performing glazing, a more efficient HVAC system, you know, that type of thing. So this is an example where we've taken the EUI from 25 down to 20. And you can see here now that because of that, the PV is more net positive than it was previously, and it's brought down the life cycle net zero to year 16. It's reduced it by 2 years. Okay. The next one, we increased the PV area by 10%. That's taken us from a 16-year life cycle net zero to a 13-year life cycle net zero. We then said, what if we change the R410A heat pumps and we put in the CO2 heat pumps? And that pretty much eliminates the greenhouse gas or global warming potential of the refrigerant. It's got rid of it altogether. So that's taken us from 13 years down to an 11-year life cycle net zero. And then the last step was to reduce the initial embodied carbon of the building. So here we said, let's put in a mass timber instead of concrete. We've taken the embodied carbon down from 60 pounds to 50 pounds CO2 per square foot. And here we are now at a 9-year net zero life cycle outcome. And I find the embodied carbon one a really interesting thing, because when I first entered the industry, like 1990, my dissertation was actually on this, and at the time, the embodied energy of the building was equal to about 3 to 5 years of operational. Okay, and in the past sort of 20, 30 years,
And that's because the energy use was really high.
that's where I'm going.
Yeah.
Yeah. So in the last 20 or 30 years, energy codes have improved, leaders come in, all this type of thing, more efficient equipment. So the operational energy use has got lower and lower and lower, and the embodied has stayed pretty static. And so what we see in a lot of modern buildings is that embodied energy doesn't equal to like 3 to 5 years. It's more like 15, 20 years of operation. And I think there's just huge potential for design teams, structural engineers, architects, and engineers to target that embodied piece. And that's the piece that really makes it the beginning. So that's it, right? How much time have we got for questions?
About an hour.
What's that?
As much as you need.
Yeah, we're way ahead of schedule. Okay. So I'll kick off, ripping off your last piece of information there. So besides going to mass timber, what other advances in embodied energy reduction are you seeing, let's say, in the more, what I would call the classic building materials, like steel and concrete?
That is my area of expertise, to be honest with you. But we've got a guy at PAE who knows this inside out, and he's got whole databases of even down to like the MEP equipment that has less embodied carbon. I know plastics are really high in embodied carbon. Certain carpets, mass timbers are big one.
There's a big one. Building open spaces where you take the material out, like a lot of our mass timber buildings, because you want to have wood exposed. You don't put in gyp and certain things that's embodied carbon that's not going into it, right? So leaving spaces more exposed.
I did see one as well. There was one strategy that I saw where they were putting concrete floors and they have like bubble forms.
Mm-hmm.
So you just, yes, pretty decent strength. It was just much less material. So certain strategies like that. I'd say we could follow up on maybe a follow up on would be strategies for reducing embodied, and we get David What came through in the chat? Did we get anything in the chat?
There's some in the chat.
Under, yeah, up in the middle of the top bar. Of course, two of them are inviting you to come ask questions.
Right.
Yeah, I have a question on that body carbon topic. Like, are the architects and structural engineers thinking about these materials in their designs, or is the client pushing for them, or?
I think, yeah.
If you could repeat the question for the people on the far end,
What's that, sorry?
please repeat the question.
Oh, so the question was, are we seeing structural engineers and architects pushing for lower embodied carbon, or is that coming from more from the client side?
Yeah.
Right. Most, I think it's coming from the architects and structural engineers. I think they're really, I think they're embracing the challenge, the architects and engineers, and they're on board with this whole thing. I think that they realise what I was describing, I think that's the whole part of this equation that's got the biggest potential for major reduction. We've reduced operational depth so much that's the piece to tie. Sometimes you work with a client who wants a super energy efficient building and they're all over it, but I'd say more comes from the architects and engineers.
I'm going to interject here. I will say that there are developers now that are developing standards for the materials. We've just recently answered an RFP where one of the requirements was that you had to be willing to engage in this process to decarbonize the concrete, because all of their buildings are made of concrete, and so they're looking for a massive reduction in the carbon footprint through that process. And there's many ways to do it. So they're just looking for partners who, as Alan was saying, are willing partners who will go through the process of finding out how and then carrying it out. But for concrete building, it's mostly your colleague, David, I think you said,
this guy called
structural
David.
engineer.
No, he's actually an architect by training, and he leads our
okay.
regenerative design group.
Yeah.
Yeah.
No, it's really, a lot of it's just about establishing databases that track the amount of carbon reduction based on the material composition of various components throughout the building. And so there's first just the setting of the standard, and typically the developers do that. And then the second thing is tracking it. We just spoke at a conference last week on this process called ESG. So it's what is it again? It's equity, environment, social. Thank you. What was the governance? And so this is about organizations developing a set of standards that is pointing towards doing the right thing. It's really the simplest way to put it. And on the environmental side, these very large developers or real estate like holding companies, they are the ones who are leading the way. Definitely the ones who are on the forefront of tracking as well, just because they have it's part of their governance to report.
Thank you.
I guess, down the line too, is there like an availability of GCs and subs that are willing to embrace these new technologies? Like think about the heat pumps that are use CO2 as refrigerant, different types of like concrete for buildings. Because, I mean, that's been done for decades, right?
It's important to the client. The client wants to do, yeah. I mean, it always comes down to cost. The contract will come back down. Do you want to get rid of that CO2 heat pump and save $500,000? It's always good. It's what the client values. Back to your earlier comment, there is a type of concrete that's being developed that actually uses CO2 in the production. Mm-hmm. So they actually, CO2, and so the potential there to have net positive concrete. So it's actually, it would go into the sequestering part of the equation. It's not on the emission side. It's actually, it's pulling CO2 out of the atmosphere, and it goes into the production of the concrete.
Right, and the beauty of that is that once it's in the concrete, it's there permanently.
Yeah.
The problem with wood is that eventually wood will degrade. It will recycle itself whether we want it to or not. And so then that carbon gets re-released. mixed, whereas the concrete just gets crushed and, laid down as gravel bed somewhere. So that concrete has really the greatest potential, but it's also because it's one of the most intensive carbon users in any structure.
I have a question. Earlier in the presentation, you mentioned CBECCOM and how it doesn't allow for modeling of heat pumps. How can anybody meet the regulatory requirement if you can't model something in the software that the state is giving you? And then because there's a two-part question. The obvious question is, well, create your own, which you guys have done and others, but that feels like a bottleneck to me. And is anyone doing anything about that?
Yeah, we sort of lobby the California Energy Commission, but they got a lot of money to create that software. It can model heat pumps in a very rudimentary, simple way. It's really sort of quite an unsophisticated bit of software. I've never used Title 24 energy modeling to inform real decisions in the building. Just use it purely because it's mandatory, you have to use it. So just use it to say, yes, tick in the box, we've complied with energy code. But any decisions about the building, we use something very different and more sophisticated. But it can model heat pumps and other technology in a very simple way, but it can't model the really cool stuff and, the heat recovery heat pumps, for example, or if you put it in geo exchange, can't do any of that stuff.
Yeah. So do you think the market is going to provide those tools, or is it already doing that?
There are upgrades. It's just slow and coming.
Yeah.
And people from industry do lobby and are pushing for this. But it's the REACH codes came out very quickly, and it's just taken it's just slow for them to upgrade the software in the Title 24 process.
Before we take that question, just to provide a bit of context, the reason, there's a reason why the state code hasn't required electrification. The state code, California Energy Commission, is under a mandate to any decisions that they make have to be financially justifiable for a certain amount of time. And so to request that everything is electrified right now, it didn't make it into the 2022 code. I'm sure it'll happen soon enough. But a lot of people are puzzled if the state has these goals, if the cities are mandating this, how come the state legally can't just require electrification? It has to be financially viable.
Basically, it's much easier for the jurisdiction to adopt REACH code and much harder to update the Title 24 software. It's like staring at the Titanic. You turn the handle, it takes 5 miles for it to move.
We all know how that turned out.
Question?
I can help this gentleman. I've been working with the California Commission for years, and they've been promising to me that they would change the air-to-water heat pump Title 24 credits. And beginning of the year, they actually did it. So both for heating, cooling, and domestic hot water. I'm not a Title 24 person, so I can't tell you exactly how it's done, but people who do it, I've had some of my friends who are consultants vet it, and they said we actually got better than what my requests were over the last few years. So it is, if you do CBEC risk, it's definitely in. The guys who use Energy Pro, and I say they're using it now. So it's basically, they only enacted it or came online end of January of this year. So if you try it out now,
That's encouraging.
you can do it. And so we're a little bit better than air-to-air heat pumps, and there is a domestic hot water component as well. As far as rebates with air-to-water heat pumps residentially, Energy Smart Homes, these are the TRCC people. I have said that they will approve air-to-water heat pumps for their program. The final documentation, hopefully I'll get it within a week. So they said they're very close to giving me something that I can hand out to people. They're still debating on the domestic hot water side, but eventually think that will come through. But the overall rebate for a Energy Smart Home, which is for PG&E, SMUD, the Southern California electric companies, is over about $5,200. You have to pull out your meter and all electric, so induction, cooktops, heat pump, dryers, and an air water heat pump that can do heating, cooling, domestic hot water. That takes care of it, all of it. And some systems only needs a 20 amp breaker or 30 amp tops. So That's what I sell.
Doable.
And it also has R32 refrigerants, so it's compliant with the next code coming up. And I've been working with the CEC last year on the commercial side of air to water heat pumps, mostly domestic hot water. They're still very confused. So anyway, things got pushed off until the 2025 code with them. But sometimes, you know what, they'll surprise you and say, you know what, we're going to do it now. But, you know, it's a grind.
Well, fingers crossed.
They move, but just not as quickly as the REACH code's been adopted, I think has been a challenge.
So the 3 years of them promising me, well, it took 3.5 years after they promised me to actually fulfill their promises. So that's how the wheels turn.
Any other questions in the room? Okay. I think that's it.
Gentlemen, thank you so much. That was very informative. Thank you.